We have 4 lectures left. What I usually do is, for most of the semester, I cruise along at whatever pace you or I feel like, without paying much attention to covering material. And then in the last couple of weeks, I freak out and I run to cover material. That is kind of deliberate, because my feeling is that covering material is not that important. You can pick it up yourself from slides, from books, from whatever. What's more important is really the discussions, the points when I ask you a trivial question, you realize that you don't really know the answer. But having said that, I kind of have to touch on a lot of things. So I'm going to try to speed things up a little bit, which means probably less interaction. That doesn't mean you shouldn't ask questions if something is not clear. But I'm just warning you in advance that I'm going to try to move faster. When we started talking about machine learning, we phrased it as learning a function from some x, or a bunch of x's, into a y. We said there is some target function out there, and we're going to try to learn it from examples. We then relaxed it a bit, and we said, well, it could be a mapping from some inputs into a function over y, a probability distribution over y, condition on x1 to xp. We still had a distinct input and distinct output. What I want to do now is move the next step, which is to blur the distinction between input and output. You can think about it as a mapping or probability distribution over jointly over x1, xp, and y, or because y is no longer different than the others, we don't need to give it a separate letter. So we could call it xp plus 1, or just talk about the distribution of these. So this becomes potentially both input and output. What I mean by this is that at different times, we may learn one function, one distribution, and then at different times, different parts of it will be known and other parts will not be known. The parts that are not known, some of it might become our output. In the terminology that we discussed at the very beginning of the course, you would call this density estimation. The full name is probability density estimation. It's called probability density estimation because the name makes sense when the covariates are continuous. And therefore, this quantity is a density, probability density function, not a regular probability mass function. But for historical reasons, we still use the word density estimation to mean the same thing even when these are discrete. So it's really a misnomer, it's not a good name. But just think about it as a learning joint distributions. Joint distributions over some set of variables. In the examples I'm going to give, the variables are going to be binary. This is just for simplicity of calculating things, giving examples. The principles are going to be the same, whether they're binary or have multiple values. If the variables are binary, how many parameters do we need to fully specify any probability distribution over p variables? How many parameters will I need to specify this fully? Every combination of values has its own probability. That would be 2 to the p. And then they have to sum to 1. So the number of free parameters, or the number of degrees of freedom, is 2 to the p minus 1. When p is even a reasonable number like 10 or 20 or 30, this is already becoming a very large number of parameters. So with a reasonable amount of data, we will have a sparseness problem. We'll have too little data trying to estimate too many parameters. This is where a problem starts. If we didn't have that problem, if the amount of data we had was enough to estimate 2 to the p parameters, we could use relative frequency. Right? We can say the probability of any particular combination of values can be estimated as the number of times this combination occurred divided by the total number of data items. Our problem is that usually that won't be the case. And if the covariates are not binary, if they are multi-valued, the problem is even bigger. And if they're continuous, it's bigger still. So this is where our problem starts. And what do we do when we have too little data to fit so many parameters? Yeah?
Stronger assumptions?
Yes, we make assumptions. So this is all going to be about what kind of assumptions we're going to make. One very obvious assumption we can make is that all the covariates are mutually independent of each other. That's a really strong assumption. If xi is independent of xj, actually I should make it stronger. If it's independent of xj, condition on any subset that does not include I and j, then, and this is for every I, for every j, then we have on the order of p parameters only. Because we can then break this to a product of individual. So a little bit like what we did in naive Bayes, except in naive Bayes we conditioned it on the label. Here there is no label to condition it on. So this represents an extreme case of everything is independent of everything else, conditioned on anything else. That's a pretty strong assumption that is, in the real world is hardly ever satisfied. But these represent just two extremes. One extreme, we don't make any assumption, we need this many parameters. The other extreme, we make extremely strong assumptions, we need only p parameters. In the real world, we look at the covariates of what they mean, and we try to make sense of them, and we can perhaps assume with reasonable confidence that some subset of them is independent of some other subset, and conversely, that two parameters are strongly dependent and we should not, or two values are strongly dependent, we should not assume independence. We can say something about it, something that's derived from the domain. So the question is, how do we capture it? How do we capture domain information, specifically regarding dependencies and independencies and conditional independencies, in a way that minimizes the number of parameters that we have to estimate, while not making unreasonable assumptions? So allowing for dependence where we're not sure, but enforcing independence where we feel fairly confident. And this is what graphical models do for us. So I'll switch now to an example from Tom Mitchell's book, which we'll use as an example from here on. This example is a story of a park, a national park, and what happens in it. And there are 6 variables. They're all binary. They mean what they say they mean. So every day there's a record kept by the park ranger of all these variables, whether there was a storm on that day, whether there was a bus tour group that visited the park on that day, whether there was lightning, whether there was campfire, there was a thunder, and whether there was a forest fire. Of course, this is maybe the most important thing. This is what they care about. But for our purposes, they care about all of them. So they might care about under what conditions are forest fires more likely. Or they might care about the relationship between thunder and campfire. Or on days when there is a forest fire, what can they say about the weather? So they could use the understanding of the relationship between these 6 variables to reason generatively, like what causes what, or to reason backwards inferentially, given what I know, what do I think happened. So the story might be that the ranger keeps record every day for a year or so of all these 6 variables. So each one of them is either a 1 or a 0 on any given day. And the story might get complicated because some days some of the record might be missing. Maybe they couldn't tell whether there was lightning or not, or maybe the dog ate it or whatever, or the bear ate it. The arrows represents the directed links, directed edges or arrows between the variables correspond to a form of dependency between them. It doesn't mean that variables that are not directly connected are not dependent or independent, but it does mean that those that are connected are dependent on one another. And the directionality of these arrows suggests causality, but it doesn't mean causality. So this is a good time to talk about the difference between causality and correlation or dependence. Correlation is symmetric. Dependence or independence or conditional independence are symmetric. Causality is, of course, not symmetric. When things are causal, they typically result in correlation or dependence of the probability distributions. But the reverse is not true. When things are correlated, it doesn't mean they're causally related. So this picture suggests causality, or in general, the kind of graphs we use suggest causality, but they're not defined as causal. They're defined as describing a set of independence assumptions. Typically, you would get these independence assumptions from your understanding of the domain and of what causes what and what is related to what. So when you see a picture like that, this is called the Bayes belief network, or a name that I prefer is the directed graphical model. They mean the same thing. Directed graphical model means the same thing as a Bayes belief network, or just a Bayes network. The structure of the network implies a number, typically a very large number, of conditional independence assumptions. I will give you the rule for how you derive conditional independence assumptions from this. The rule is, for every node x, xi, when conditioned on all the parents of xi, is conditionally independent of all the non-descendants I'll explain in a minute. minute what I mean descendants of xi. Non-descendants. So non-descendants is anybody who you cannot get to from u by going down. So what is, let's take an example, campfire. Campfire, when conditioned on all of its parents, namely jointly on storm and bus tour group, is independent of all the other nodes which are not its descendants. Which nodes are not descendants of campfire? Where it's lightning and thunder. Forest fire is, of course, a descendant. Take bus tour group. Bus tour group, when conditioned on its parents, which are its parents? The null set. So when conditioned on the null set, which in other words, when not conditioned, is independent of all of its non-descendants, which are all the nodes except campfire and forest fire, and so forth. You can go over and make a list. Maybe we should do that a little bit. You tell me, storm. What is storm independent on the condition on nothing? Just the bus tour group, right? That's the only non-descendant. What is thunder independent of? When conditioned on, thunder has to be conditioned only on lightning. So remember that parents means direct predecessors, only one layer up. Non-descendants or descendants means children, grandchildren, great-grandchildren, and so forth. What is the thunder independent on when conditioned on lightning? Just everything, right? All thunder, when conditioned on its sole parent, is independent of all of its non-descendants. It doesn't have any descendants, so it's independent of all of these, right? So it's independent of bus, storm, lightning, storm, not lightning, campfire, and fire, forest fire. The graph that is described this way is a directed acyclic graph, a DAG. What we're describing by the set of conditional independence assumptions is a hard bias. Because we're not saying how particularly variables are dependent on each other. We're not giving the form of the solution, but we're putting constraints on what the solution might look like. Any function might be a solution as long as it satisfies all these independence conditions. So we're putting conditions on what the solution might look like, hard conditions, and in other words, it's a hard bias. Very roughly speaking, each one of these conditions might, maybe not true, but it might correspond to reducing the number of parameters by one or more parameters. So the more conditional independence assumptions you can make credibly, the fewer the number of free parameters you have left. So you want to impose as many of them as possible. Imposing as many as possible means coming up with a graph, that has relatively few edges. So this is a little counterintuitive. Hey, what's happening here? A little counterintuitive. The more edges you have, the less independence you have, right? The purpose of this graph is to convey independence, a set of independence assumptions, but it's conveying it by putting edges where there actually are dependencies. Now, every time there's an edge, there is a dependence. That doesn't mean that when two nodes are not connected, for example, these two, it doesn't mean that they're not dependent. That's an important point. Two nodes that are connected by edge are dependent. They're not independent of each other. But two nodes that are not connected by an edge may or may not be dependent. We need to figure that out from the graph. And I'll give you some rules for figuring it out. Before I do that, let me use the graph to factor the likelihood function. Factoring the likelihood function would be an alternative way of representing this graph. So the most general likelihood function, in this case, is expressed as probability distribution over 6 variables, and I'll just give them first letters. S, B, L, C, T, and F. This is the most general form of the joint distribution. And as we said, it has 2 to the 6 minus 1 free parameters. But given the assumptions embedded in this graph, we can break it down by starting at the top of the graph, namely at the, if you have a DAG, you can order the nodes in order of, that does not contradict the direction of the arrows. There's no single unique ordering, but you can choose one. We'll just take storm and then bus tour troops. We could have done the opposite, right? This will be probability of storm times probability of bus tour group. And let me start by conditioning it. Let me first break it down without making any assumptions. Times probability of lightning given the previous 2 times probability of campfire given the previous 3 times probability of thunder given the previous 4 times probability of fire given the previous 5. All right, what I did here was just a chain rule. For this, I did not need the graph. This is true for any probability distribution, whether or not it satisfies any conditional independence assumptions, right? Now I'm going to write next to it the same thing, but taking advantage of my conditional independence assumptions. This would remain P of S. This would become P of B, because B is independent of S conditioned on the null set. So I'm taking advantage of the fact that the bus tour group is independent of storm, according to my graph. This would become P of L conditioned on its parents, which is storm. So I managed to get rid of the dependence on B. And again, this is because, by our rules, when you condition on the parent, you become independent, condition independent of all your non-descendants. So I use that rule to simplify this into this. I drop the dependence on one of them. That means I would have fewer parameters to estimate. This would be probability of, what is C? Campfire. I have to maintain, of these 3, I have to maintain the true parents, which is S and B. But I can drop the dependence on L. For thunder, I have to maintain the dependence on L only. That's a big win, because I can drop these 3. The more you can drop, the fewer parameters you will have to estimate. And then finally, probability of fire given dependence on its parents, which is L, S, and C. So I could have written this down directly from the graph. Just write down the nodes in an order consistent with the direction of the edges. And for each node, condition it directly on its parents. But I wanted to show you how it relates to the same factorization that does not make any assumptions. This is where we gain strength. This is where we reduce parameters. We still need to estimate all of these. How many parameters do we need for estimating all of these? How many parameters do we need for estimating? How many free parameters do we need for estimating this? From data. How many free parameters are there here? This is a binary variable. One free parameters. Probability of there's a storm or no storm, they have to sum to one free parameter. Here's 1. What about here? 1. What about here? S could be 0 or 1. When S is 0, we need one free parameter to estimate the probability of this under this condition. When S is 1, we need another one parameter. So it's 2. Here, there are 4 combinations of these values, and each one of them results in a particular binomial distribution here, or Bernoulli distribution here. So there are 4 free parameters. Here there are 2. And here, there are 8. The total number of parameters is the sum of this. 10, 14, 16, 17, 18. 18 as opposed to 31, which is what we had before. What happens if these covariates are not binary? Let's say they're tertiary. Every one of them can have 3 values. How many parameters would we need here? 2. How many parameters here? 2. How many parameters will we need here? 3 possible values here. For each one of them we need 2. So that's 6. How many would we need here? 3 possible here, 3 possible here. So there are 9 possible conditioning situations. For each one of them, we need 2 parameters to capture the distribution of this trinary. So 9 times 2. And different variables can have different number of parameters. The important thing is that once you fix the variables, the number of free parameters depends most crucially on the number of things you're conditioning on here, of which this is the worst offender. So in other words, the node that has the largest number of parents tends to have the most parameters to estimate its distribution. Of course, if you have 5 parents, but they're all binary, and somebody has 2 parents, but they each take on 10 values, then that doesn't hold. But generally speaking, if all the covariates are binary, then the number of parents, and in fact the number of parameters grows exponentially with the number of parents. So this is a very critical point. If you have 100 nodes, and you have a network such that each, let's say 100 binary variables, and in one network, each node has 5 parents. Okay. In another network, most nodes have 1 or 2 parents, but one node has 20 parents. The number of parameters you'll have to estimate for the second node is probably going to be larger. So it's the maximum number of parents that is really the determiner of the order of the number of parameters you're going to have. So beware of maximum or watch for maximum number of parents. What you see here is an example of the actual probability distribution, conditional probability distribution for one particular node, which is the campfire node, which is this one. We say here that it depends on 2 binary conditioners, and therefore it has 4 free parameters, 8 parameters, but only 4 of them are free. And you can see them here. Here are the 4 conditions over the parents, S and B, SB, S not B, not SB, and not S not B. And for each one of them, there's a distribution over the campfire, a binary distribution in a column. So each column is one particular conditional distribution, and it has only 1 degree of freedom, 1 free parameter. If the covariates are continuous, or some of them are, instead of having a table, you might have some familiar distribution like a Gaussian or a beta or a uniform or anything like that. You would find some other way of specifying the distributions. The ideas would remain the same. That you're now estimating distributions with relatively few conditioners. Questions so far? Let me go back to this issue of how dependence flows in the network, how influence flows in the network. I mentioned that the fact that these 2 are not connected doesn't mean they're independent of each other. So we may not be able to write just thunder is independent of forest fires. It may not be true. So let me go over specific examples of substructures that you find in a network such that once you learn all these substructures, there are only 3 of them really. Once you learn them, you can apply them to any network. The example I'm going to give comes from a different source, but it's a very famous source. So you'll probably encounter it in books and other places. So my example is of nodes called sprinkler and rain, and the grass being wet grass. Let me start by saying that when it rains, the grass tends to get wet. Tends to. We live in a probabilistic world. It's possible that it's so hot or there was some awning or something that it didn't get wet. But definitely there's a relationship between the 2. And we believe it's a causal relationship. For our purposes, the 2 are not independent. There's another way the grass can get wet. If the sprinkler is running. You know what I mean, right? Okay. So there are 2 possible causes for the same effect. Now, looking at this without looking at the common effect, just looking at the sprinkler and the rain, we can start by assuming that the 2 are independent. Let's say that the sprinkler comes on with a nice little random number generator every day with some probability. Okay? And the rain comes on with some probability with also random number generator. Of course, that's not true, right? I mean, sprinklers are turned on by people and they may take into account whether it's going to rain or not. But let's say that the landlord is absent, is out of the country, and is set his sprinkler to come on without knowing anything about the weather. So we're going to assume that sprinkler and rain are independent. Now suppose we know that the grass is wet. Do sprinkler and rain continue to be independent? The answer is no. I'll give you the intuition first. If you see that the grass is wet, you say, aha, either it rained or the sprinkler was on. And now you're in a position to learn from one about the other. For example, if it didn't rain, you all of a sudden believe much more strongly that the sprinkler was on. Or if you knew that the sprinkler was not on, you believe very strongly that there was rain, right? You can take it to an extreme. If the grass can only be wet if at least one of these is on, then knowing that one of them is not on makes you sure that the other one is on. But in the more moderate version of this, you may not be sure, but the probability estimate might change. So when you see a common effect, it creates a conditioning between the possible causes of that effect. Another way of saying it is that if you see the grass is wet, and then you see that and then you suspect that the sprinkler might be on, or the rain might have been on, or both. But then you investigate and you find that it did rain, you no longer need to assume the sprinkler was on. This was a sufficient explanation, and therefore it will reduce your belief in the sprinkler being on. Let's make it even more realistic. Let's say that the sprinkler comes on very, very rarely. Let's say the rain comes on very rarely. Okay, you are in, Arizona? You're in Arizona, and these are really rare events, both of them. Now you see the grass is wet. You say, aha, one of them must have happened. Maybe both, but that's very unlikely, right? You find out that one happened, you said, okay, that's probably the reason. I don't need another one. This phenomena is called explaining away. What it means is, seeing that there's a rain explained away the need for the sprinkler. Doctors do it all the time. You come with a bunch of symptoms. There could be multiple diseases that could produce these symptoms. They suspect some of them. Maybe they go with the one they suspect is the most likely. They do some test. They find that that condition really is present. They don't keep on testing for the others. They found a sufficient explanation. And therefore, there's no reason to suspect the others. They found an explanation, so they explained away the rest. So, sprinkler is independent of rain, but sprinkler is not independent of rain when you condition it on its joint effect. This is also called the V structure because of this V. Now let's look at an inverted V structure when you have a single cause and two effects. Here you have two causes and a single effect. The single cause is going to be prediction of a cloudy day. Cloudy day means that you look out in the morning and it's cloudy. Well, if it's cloudy, that means whether it's cloudy or not changes the probability that it's going to rain. It could rain under either condition, but it's more likely to rain if it is cloudy. Similarly, it changes the probability that you would choose to turn on the sprinkler to set the sprinkler on or not. So seeing a cloudy day affects both of these things. Let me write explaining away somewhere else. This is explaining away. Now let's look at these relationships. In fact, because whether it's cloudy or not affects both of these, we have reason to believe now that these two are dependent on each other. Right? So I'm going to ignore this story and just focus on this story. Because they have a common cause, when things have a common cause, they tend to lose their independence. Think of the two tests that we did in our Bayes example of cancer. The cause of the errors were laboratories, technicians, type of test, and so forth. Whenever there's a common cause, there's dependence. So because there is at least one common cause, we suspect that the sprinkler is not independent of the rain. Assuming now that the sprinkler is the only common cause, by conditioning on it, we make the two of them independent. What's the intuition behind it? If I told you that the reason sprinkler and rain are correlated is because they both depend on whether the day was cloudy, but not on anything else in common, then on days that are cloudy, there's going to be a decision made here that is going to favor not using the sprinkler. And there's going to be a decision made here by the gods of weather favoring that will be rain. But how that decision proceeds, it's a probabilistic decision. How that decision proceeds will not affect how this decision proceeds. Once this is determined, once it's determined to be cloudy, once it's determined to be not cloudy, it's the same thing happens. So once you fix the value here, these two become independent unless they have some other parent in common, another common factor that affects them both. But assuming they don't, assuming this is the full story, not conditioning on this means they're dependent. Conditioning on this means they're independent. So it reverses the story we had before. So this is independent. When conditioned on, this is independent, and then when conditioned on cloudy day, they become independent. Appreciate the reversal here. When you have a common cause, you become dependent unless you condition on that common cause. When you have a common effect, you are typically independent unless there's something above you. When you have just a common effect, you're independent unless you condition on a common effect. In other words, a common effect can allow influence to travel through it. Whereas a common parent, it's the other way around. So I have a way, I wrote it down a particular way. Influence travels through a common effect only if it is known and a common cause only if unknown. So this is an alternative way of remembering this. Influence travels through a common effect only if it is known, and through a common cause only if it is unknown. There's one more structure that we need to study in addition to these two, and this would give us enough to go over the entire network. And that structure is a very simple chain structure. A causing B causing C. So let's take cloudy, sprinkler, and wet grass. Or let me just separate it from this completely. Let me make it just A, B, and C. Again, this does not formally mean that these cause one another. It's just a way of encoding conditional independence assumptions. What conditional independence assumptions are encoded in this structure? Every node is independent of all of its non-descendants. Well, everybody is its descendants, so can't do it with A, right? Let's try B. Every node, when conditioned on all its parents, A, is conditionally independent of all of its non-descendants. Well, C is its dependent, so we can't do it with B. So what about C? C, when conditioned on its parent, which is B, is independent of its non-descendants, which is A in this case. So the only conditional independence assumption embedded in this chain is this one, that grandpa and grandchild are independent when you condition on the parent in between them. Now, is this true? No, it's not. Because A influences B and B influences C, A influences C. So this is an example that is more similar to this case, where conditioning makes them independent, but not conditioning does not make them independent. So I'm going to add one more rule here, which is number 3. Influence travels through a common effect under these conditions, a common cause under these conditions, and a chain only if middle node is unknown. If it's unknown, so we're here, then they're not independent, influence travels through. Some people, when they teach Bayes nets, they use something called the Bayes ball. It has to do with taking a ball, a physical ball like a tennis ball, and seeing whether you can make it travel through the different nodes. So you would put the ball in one of these places and you try to go up and down to different places, and there would be rules of when the ball can go or not. The ball corresponds to having influence, namely to having dependence. I prefer to use these rules. But it's the same thing. They embody the same idea. What is the expressive power of directed graphical models? Now we're talking about hard bias and representation power, expressive power. Can directed graphical models represent any function? William?
I don't think you can represent like three mutually independent events.
Three mutually independent events.
Or binary random variables.
So mutually independent events, why not? Why not just represent them as A, B, and C with no arrows?
I meant to say mutually dependent.
Mutually dependent.
What distribution has seven parameters?
Okay. So William is suggesting that you cannot represent a situation where the full 7 free parameters are employed, namely where everything depends on everything else. Anybody wants to agree or disagree? Are you saying only for 3 or for any n greater than 3?
I think you can represent it if you just break the rule of you just break the DAG structure. Yeah, you break the DAG structure and you will get a cyclic graph, which looks weird.
So you're saying with a cyclical graph you can, but then it's not a Bayes net. Can use the board now. Anybody wants to disagree that you cannot do it with a Bayes net? Well, I'll disagree. You want to disagree?
Yeah.
How would you do it?
As long as you have an edge between and like it's really better in the direction because like it's symmetric property whatever.
I'm sorry, I didn't hear the end. I'm preparing to write down your solution. Tell me where to put A. Well, I can put all 3 of them, and then you tell me what to do. Cannot? Okay. Well, I think you can. Not just 3, any n. So this would be very simple. A goes to B, A goes to C, and B goes to C. Let me write it in a slightly different way. Let me say that A goes to B, and then B goes to C, but so does A, and then C goes to D, but so does A and B, and so forth. And then E, B. So every time you add a new node, you connect all the parents to it. What it means in terms of factorization is that you have P of A times P of B given A times P of C given A and B times P of D given A, B, C, and so forth. And this you will recognize as a regular factorization that is not making any assumptions. So yes, there is a Bayes net that corresponds to the completely unconstrained distributions, namely it embeds no independence assumptions. That was not exactly the question I asked. I asked about the bias of directed graphical models of Bayes nets. And what I got here is an example of one Bayes net that can express any function. So in other words, this Bayes net has no hard bias. So the question I asked, admittedly, is confusing because every particular Bayes net, every particular graph is not a single function. It's a family of functions. Every single Bayes net embodies a particular hard bias. This one embodies the hard bias of null, no bias. Anything can be expressed. But a Bayes net that has fewer edges says that the function could be any one of a very large number of functions as long as they satisfy those conditional independence assumptions. So the space of base nets is the space of different biases. Each one expresses a different bias. And now you can think about DGM as a language. DGM is a language for expressing conditional independence, or equivalently, hard bias. Now you can ask the question, is it a complete language? Can any set of conditional independence assumptions be expressed in it? And now the answer is no. So as a language, it has a bias. This is confusing. This is not the same bias that we're talking about in the space of functions. Until now we talked about the bias in the space of functions. Now I'm giving you a very rich language for expressing biases. And I'm asking the question, can you express any bias you have in mind? And the answer is no. It's a particular language. Languages have representations. Representations have consequences. I'll show you later when we talk about undirected graphical models that it's a different language for expressing a different family of biases, and that the two are somewhat overlapping but also somewhat separate. There are things you can express in one that you cannot express in the other. What are DGMs good for? In general, not just for DGMs. In general, if you have a way of calculating P of x1 through xp, you can use it to calculate a variety of other things mostly by operations of marginalization. So, for example, you can calculate any subset of these. For example, P of x3 equals some little x3, and x5 equals some little x5. You can calculate the probability of this thing by marginalizing away all the other variables. Specifically, it would be a sum over all possible values of x1, x2, skip x3, x4, skip x5, x6, all the way to xp. So you sum over all possible combinations of the other variables of this joint. x1, x2, x3 equals the specific value that we gave it, x4, x5 being the specific value, x6, xp. Okay, this is called marginalization. So keep in mind that if you have this, you can calculate anything that looks like this. But this summation can be a killer. The number of terms you're summing over here, or the number of combinations that you have here, is exponential in p, right? Specifically in p minus 2, but that's the same as p. Can be exponential. The calculation may be exponential. You may find a way of doing it that would be more efficient, but there's a possibility that you'll get stuck because you're summing here over an exponential number of terms. Keep that caveat in mind. Another thing you can calculate is something like just x3 and x5 without specifying values. This gives you back a number. a single number. This gives you back a distribution over two variables. But it's a general case of this. You can basically repeat this calculation for each possible combination of x3 and x5. So it's the same thing. Same thing in the sense that you can do it by marginalization, but it could be exponential. And of course, you can also do things like a combination of the two, where you are interested in the probability of x2 and x4 under the conditions that x3 is some value and x5 is some value. And again, you can do it using this. So you specify some of the values, and you want to know the distribution over the others. A general way of looking at this is to take the set of all of your variables from 1 to p and to break them into 3 sets at any one time after you've learned the joint distribution. The set of variables you care about, the set of variables whose values you know already, and the set of variables you don't care about and you're going to marginalize over. Let me reorder that in a logically better way. The set of variables whose values you know already. So this will be one set here. Values known. I'll call it x sub k for known. The set of values you care about, you want to know, call it want to know. I'll call it x sub t for the test variables. You can call it anything you want. And the values that you don't know and that you don't care to know in this particular case. So these are to be marginalized over. And I'll call those x sub m. So the full set of x1 through xp is broken down into 3 sets: x known, x want to be known or want to know something about, and this is x to be marginalized over. The beauty of this approach, as opposed to what we've been doing until now, which is identifying something in advance as input and output. The beauty of this approach is that you don't specify that in advance. You study, you try to come up with some estimation of this function, and from this function, you can now define different subsets to belong to any one of these 3. You can very roughly say that maybe these are the inputs and these are the outputs, and these are the don't cares or the latent. So say input, output, and latent. Latent means you don't know their value, they're hidden, they participate somehow, but you will be marginalizing over all of their possible values. But input and output might be different in different situations. Sometimes you know some things, you know others. So under this kind of notation, we can ask the following questions. Given some values, which we chose to call x sub k, just to make sure to clarify, this is a set of variables, not a single variable, right? X sub k. Calculate posterior distribution over some other set. Which we called x sub t. So this would mean calculate p of x sub t given that x sub k is equal to some values. So you have a network like the park example, and you know that there was lightning, and you know that there was a school bus, and you want to know the probability, bus tour group, and you want to know the probability that there was fire. That would be one example. So the lightning and the bus tour group would fall into xk, you know their values, and x sub t would be the single variable fire. So any one of these x's could be a set, but a set could be also a single variable. So you can use it to estimate, we call them posterior probabilities because they're posterior to seeing this part of the data. If you think of this as the input and this is the output. A second thing you can do that's related to this is given some values, calculate most likely values of some other set. This would be argmax over this other set of p of xt given that xk has some values. So it's the same thing, but instead of returning back the full posterior, the full distribution over this set of variables, you're returning a particular value of the set of variables. If this is a single variable, you're returning a single value. If this is two variables, you're returning the joint two values of the two variables that have, of all possible combinations of values of these variables, have the highest posterior. These two things together are called inference. Or more generally, or more accurately, probabilistic inference. Inference means you have the model in your head or in your hand, a joint probability, and now you know some things and you want to learn about some other things. You know the variables that I called x sub k. You want to learn about the variables that are called x sub t. Learning about them can come in one of two flavors usually. You want to know their full probabilistic distribution, posterior distribution, that's Q1, or you want to know the most likely assignment. If you think for a moment about hidden Markov models, which algorithm does this? Viterbi. In the hidden Markov model, the known part corresponds to the observables, the O's, right? These are the O's. The unknown part corresponds to the state Q. There are no latents in this case. But HMMs are pretty rigid in the sense that the observables are always observed, that's why we call them observables, and the states are always unobserved. But in the most general case, you don't have to determine that in advance. You can ask that inference, you can do inference with any subset of the variables. But keep in mind the computational complexity might be problematic because doing these things requires marginalizations, and those marginalizations are over potentially exponential number of combinations. Q3 is going to be the question of parameter learning. Given a network which is the same as saying a bias, which is the same as saying a set of conditional independence assumptions, and data learn P of x1 through xp. This is the problem of learning the values of the parameters from data. It could be easy or it could be hard. If the data is complete, this is typically easy. If the data is incomplete, different elements are missing for different records, this could be hard. I'll go over this in more detail later. This is called parameter learning. So this is, whereas this is called inference. The first two are inference. In the HMM case, this is the forward-backward algorithm, or the Baum-Welsh algorithm. And then the last question we like to ask is, you're not even given a network. You're not given the bias. You're not given a set of conditional independence assumptions. You want to derive independence of variables or conditional independence from the data. Given only data, derive or detect or identify conditional independence assumptions. Not assumptions anymore. Derive conditional independence assertions. This is called structure learning. Structure learning is basically learning the structure of the Bayes net. Now, if you were paying attention, you should at this point raise your hand and say, but you taught us it's impossible. Because learning a structure basically means learning the bias, which means starting with no bias. Right? And you would be right that if you started with no bias, it is impossible to successfully learn, or it's impossible to be guaranteed to learn conditional independence assumptions. There would be situations where you'd get lucky, of course. It's always possible. But we don't start from scratch. The way we do structure learning is by making some assumptions, some prior over biases, and that becomes our new soft bias. But it's much harder. It requires a lot more data. We'll get to it when we talk about the specifics of each of these. For now, I just wanted you to have the terminology. We have inference, parameter learning, and structure learning.